Hi, in this lesson, we're going to continue our work from Unit 8 and learn how to simplify expressions with exponents and roots. We will begin by simplifying expressions with exponents, then move on to rational exponents, simplifying radicals, and finally complex numbers. Our objectives are to apply properties of exponents to simplify expressions, work with negative exponents, work with rational exponents, simplify square roots, and write complex numbers in exact and approximate forms. At 8, we learned several of the properties of exponents, including multiplying powers with the same base, where we just add the exponents, dividing powers with the same base, where we subtract the exponents, beginning with the numerator and subtracting the denominator, finding the power of a power, where we multiply those exponents, negative exponents, which basically meant that we were in the wrong part of our fraction, and then using 0 as an exponent. Now we're going to add 3 more properties to what we already know about working with exponents. If I'm going to raise a product to a power, in other words, the quantity AB to the n, we're going to distribute that exponent to each of those factors. And so now the quantity AB to the n becomes A to the n times B to the n. Raising a quotient is very similar. We're also going to distribute that exponent to the numerator and the denominator. So A over B to the n becomes A to the n over B to the n, with the exception that B cannot equal 0. For negative exponents, we already talked about these last two. If I have b to opposite of n, that's the same thing as 1 over b to the n, and 1 over a to the negative or opposite of n becomes a to the n. We can also do a cute little shortcut here if I have a fraction and I'm going to raise it to a negative exponent. So a over b to the negative n is the same thing as b over a to the n. In other words, I'm taking the reciprocal here, which is the same thing I did in this case and in this case. I just did the reciprocal. And so this little shortcut can come in handy in our future examples. I do want to add a couple of notes that go with this chapter. We're going to have to make some assumptions so that we don't have to worry about violating some of the rules of exponents. So for this chapter, no base is going to be equal to 0. No denominators are going to be equal to 0. And unless otherwise noted, all numbers we use are real numbers. When we get to the final section on complex numbers, we'll change that up. On this slide, we're going to review some of the rules we already learned in Unit 8 and simplify some expressions. So this first one is 5 times x to the 0. And if you recall, anything to the 0 equals 1. So this is the same thing as 5 times 1, or just 5. Again, this is something taken or to the power of 0. I really don't need to work with this because it would simplify and then raise to the 0, it just equals 1. For this one, we are taking r to the third times r to the ninth. We have the same base, so we can just add those exponents together, and that's going to be r to the 12th. On this final one, really those parentheses are just kind of separating out that we're starting with another number. There's really no other purpose for them. So I'm going to remove them, but at the same time I'm going to rearrange and put my integer values first. And then I'm going to take my variable terms and put them in alphabetical order so I can organize them. So I have a squared, I have another a, then I have b to the 5th and b to the 9th. So 3 times 7 is 21. I have A, I have two of them plus one more. I have a B to the fifth, and I have 9 more. So that gives me 21, A to the third, B to the 14th. Now we're going to go ahead and apply some of the new properties that we just learned. So we have a rational expression. We have 4a to the 10th, b to the 5th, over 6ab squared. So we're going to go ahead and just simplify that 4 over 6. That's going to become 2/3. Now all of these are positive, so I'm going to go ahead, a 10, and then this is 1, so I'll subtract 1 out on that one. And this 5 is bigger than the 2, so I'll go 5 minus 2. And that's going to become 2, a to the 9th, b to the 3rd, and that's going to all be over 3. For this next one, it's actually integer values, but that is the same thing as 5 over 7 times 5 over 7, or using our properties of exponents, we can distribute that squared to make that 5 squared over 7 squared, and then we get 25 over 49. For this last one, we're going to distribute that power of 4 to the numerator and the denominator. So that's going to become x to the 5th times 4 over y to the 3rd times 4. Simplifying those down, we get x to the 20th over y to the 12th. On this slide, we're going to practice using negative exponents. That first one is 1 over b to the negative 3. So instead of using the negative, we can make that a positive 3 and take the reciprocal. So doing that, that just becomes b cubed, or b to the 3rd. Now for this one, remember that little shortcut. We can make this exponent a positive, make it a squared value by taking the reciprocal inside here. So we're going to go 7/5 squared, and then we're going to distribute that squared to the 7 and to the 5, and now we get 49 over 25. This last one, we have some positive and negative exponents, so the easiest way to do this is just go ahead and make that fraction bar out. We have the 2 and the 3. Those are already simplified. Anything that's positive, we will write to the top. Anything that's negative, we're going to take the reciprocal and put it down here into the denominator. Now we're going to move on to rational exponents. So instead of just rational expressions with exponents, the exponents themselves will be rational. In rational exponents, the numerator is the power and the denominator is the root. For a basic one, we can have x to the 1 over n, which then would equal the nth root of x. In a more complicated example, we could have x to the m over n, and in this case the n is the root, and we would just write it here, and then the m is still the power. Now you can write that either outside or inside with the x. It will give you the same value. Sometimes it's easier to work with it in one form or the other. This n right here is called the index. And we don't write it when we're working with square roots. It's the most common one. So if there's no number in a radical sign like that, we just assume it's the square root. But sometimes we need other ones like the 3rd root, the 4th root, and so on. So that n value is very important. It will tell us which root we are dealing with. Okay, for this slide, we're going to actually use numeric values, no variable terms here, to show you how simplifying rational exponents actually works out. So if I look at this first example, I have 8 to the 4/3. Now, honestly, all of these, you could put these in your calculator. So I'm going to write it up here on the top. So you could put 8, use that caret button, which raises something to a power, and put in 4/3, and you will get the answer that way. If it is not a value that simplifies nicely, you're going to get a lot of decimal places, and sometimes that is what you want to do. But let me explain how this actually works. So I'm going to go back to this idea of using our properties of exponents and how we multiply things. So this really is 8, and I'm going to take it out to the 4/3. I'm going to rewrite that 8 as 2 times 2 times 2, or 2 to the 3rd to the 4/3. And so that really means 2, and I multiply these together, times 4/3. Notice that's going to cancel out, and I get 2 to the 4th, which equals 16. Now, using radical expressions on this, this would have been, I'm going to rewrite that 8 as 2 to the 3rd, but 2 to the 3rd would be inside the radical, and then we want the 3rd power, and that whole thing is raised to the 4th. When we have this number here, the 3rd root, and that 3 is called the index, canceling out or matching the power inside the radical, basically they work as opposites. They're inverse operations. And so whenever our exponents match, we can pull that value out and remove the radical, and we get to the 2 to the 4th. Now I can explain this a little more when we meet in person. Honestly, I would be using this idea of working with them as fractions and keeping them in that fractional form. It actually works out quite well. So that's what I'm going to do for the next one. So 81 is the same thing as 9 times 9, and 9 is the same thing as 3 times 3. So I have 3 times 3 times 3. So 81 actually is 3 to the 4th. So what I have here is 3 to the 4th to the 34ths. So I can rewrite that. Remember, I'm just multiplying. So I have the 4 times 3, and that's over 4, which just gives me 3 to the 3rd, and that equals 3 times 3 times 3, or 27. For this one here, this last one, it doesn't work out super friendly, really, but I can rewrite it so I can put it in my calculator and get an approximate answer. So again, that 12, that base is still going to be 12. This is still the power, and the root goes like this. So I could take 12 to the 3/4 and put that in the calculator and get an approximate answer. If you tried to factor out the 12, I mean, that is 4 times 3, or 2 times 2 times 3, and really nothing. Notice there's no 4th power in there to get any radicals canceling out. But I can get the answer in the calculator, which is, like I said, going to have a whole bunch of decimals here, and it is 6 point. Let me write this out. I'm going to put the approximate, because I'm going to be rounding. It's 6.447, and then the next digit is 4. So this is rounded to 3 decimal places, and it just keeps going on and on. It's an irrational number. For this section, we're going to work with simplifying square roots. So most of you are familiar with your square roots of your perfect squares. So if I were to multiply, for example, 12 times 12, I get 144. So the square root, or the principal positive square root of 144, is 12. And we're going to be working with those positive square roots for this. If you're not familiar with these, I suggest you write them down somewhere and get used to them. Super important to know these. To simplify a square root, you're going to factor any composite number within the radical sign into products of perfect square numbers. Now, sometimes not every number is going to be a perfect square, but you're going to try to find as many of those as you can. You will take the square root of each of those perfect square factors, and any non-perfect square factor is going to stay inside the radical sign. For this first example, we're going to take the square root of 360. So the first thing we want to do is to find a perfect square, and 36 is a perfect square number. And that one factors quite nicely in this example. So we now have the square root of the product of 36 and 10. We can break that apart for step 3. That is optional. If you want to go straight from step 2 all the way to 4, you can. And what we're doing is basically taking the square root of any of those perfect squares. So the square root of 36 is 6. 10 is not a perfect square. We're going to keep that number inside the radical. So the square root of 360 in exact form is 6 times the square root of 10. I tend to call that 6 rad 10. That's just a habit from California, but you could just say it either way. So if you have a prime number, 17 cannot be factored, and there isn't anything. And in this case, that is the final answer. So you can't factor 17 down any further, so there are no perfect square factors to be able to pull out of that radical. So that one is just the square root of 17. For this example, we now have a radical within a fraction, and specifically this one's in the numerator. Now the radicals could actually be in the numerator, the denominator, or both, and they're handled the same way, where you simplify the square root themselves and then work on. So let's start with this simple one where we have the square root of 50 divided by 2. So we're going to break 50 into 2 times 25 because 25 is a perfect square. We're going to pull that perfect square out of this radical and it becomes 5. The 2 we're going to leave, that's a prime number. You can't take a square root of it. And this becomes 5 rad 2 divided by 2. Now that 2 inside the radical and that regular 2 outside do not simplify. That right there is the simplest expression we can get. So here's another one where we have the square root of 24 over 4. And we're going to break that up into 4 times 6. 6 does not simplify any further. We cannot take a square root of it. We have 2 times 3. Neither of those are going to help us much, so we're just going to leave that alone. But we can take the square root of 4. And so for step 3 there, you see that we now have pulled that 4 out and we have 2 times square root of 6, 2 rad 6 over 4. Now that 2 and that 4 can simplify. And since these are products, it's okay to cross cancel and just go ahead. Well, there's 1 there. We can take the 2. Now, if we were adding or subtracting here, that wouldn't work, but in this case it does. So our final answer is rad 6 divided by 2. Now for this one, we do have a sum within our numerator. So it's going to be a little trickier when we go to simplify it. So we have 2 plus the square root of 80 all divided by 2. I'll work with the square root of 80 first, and that is the same thing as 5 times 16. So now I can pull out that 16 is a perfect square. Square root of 16 is 4, but the 5 stays in there. We can't simplify that. So now I have 2 plus 4 rad 5, all divided by 2. I'm going to break this into its components because this is now 2 over 2 plus 4 rad 5 over 2. The 2 over 2 becomes a 1. We can simplify this way, and so now I get 1 plus 2 times square root of 5 as my final simplified answer. Now here's 4 problems. They're kind of mixed up, and I want you to try these. So please pause the video, work the problems. I'm going to do them one at a time with a little bit of a pause in between. So if you want to check your work as you go, that is absolutely fine. I'm going to work them in order. So for this first one, it is the square root of 1,800. So what I'm going to do is break this into components. So that's the same thing as 18 times 100, and I've noticed that that 18 actually can be broken down a little more. So that can be 2 times 9, and 9 is also a perfect square, and then I have 100. So the square root of 2 isn't going to go anywhere. Square root of 9 though is 3. The square root of 100 is 10. And then I have square root of 2 left over, so that becomes 30 rad 2. For the second example, 7 is a prime number, so I'm already done. That is in simplest form. That is just the square root of 7. For example 3, we have a radical in the numerator divided by 5. So I'm going to take 300 and break that down into 3 times 100. And that's all over 5. 3 is going to stay within the radical. The square root of 100 is 10. And that's divided by 5. And again, this is a product here, so I can simplify that, and that's going to become 2 rad 3. For our final one, we are going to work with a difference. So we have 4 minus the square root of 8, all divided by 2. So here we're going to go ahead and go 4 minus, and 8 can be broken into 2 times 4, and 4 is a perfect square. That's going to be divided by 2. So I have 4. I'm going to go ahead and write this one already, break it up. We have that sign. We're subtracting. We have 2 rad 2 over 2. This becomes 2 minus the square, 2 minus the square root of 2. At our final section, working with complex numbers. Now, in an earlier slide, I said for this lesson, until I tell you differently, we are going to assume all numbers are real numbers. This is that time when we're going to take that rule away, and we're going to work with non-real numbers. So a complex number is a number in the form a plus bi, such that a and b are real numbers, but I is the square root of negative 1. I squared equals negative 1. Now before, we've always had, if you square a number, it's going to be positive, but I is an imaginary number, so it's not going to use the rules that we are normally thinking of when we talk about our number systems. And this is going to allow us to take square roots of negative values by factoring out a -1, finding a real part. Now, sometimes in working with complex numbers, we only have b times I. Sometimes we have the a real part, plus the bi. So you're going to see a little bit of variety here. This chart here shows you the number systems that you have worked with. We start in the middle with our whole numbers. Sometimes people will even take that down further to counting numbers like 1, 2, 3. Whole numbers add in 0. Integers, all of a sudden we have whole numbers and their opposites. Real numbers, now we can put them on a number line. They include rational and irrational numbers. If I take a square root of a number and it's not a perfect square, it's irrational. Pi is irrational. Complex numbers have an imaginary part, and we have to use that unit I. Notice these 3 examples across the bottom here, and that kind of illustrates what I said, that even though they come in this form of a plus bi, in this one we just have the bi. This one still, even though it's just -5, we just have the a part. And here 2 plus 8i, we have all of it. All of these still are considered complex numbers, even though that -5 is also a real number and does not have an imaginary part. So now we can simplify square roots of negative numbers, and this kind of completes working with these radicals. So what we're going to do is we're going to factor out a -1. So now I have -1 times 16. 16 is a perfect square, and that is 4. And the square root of -1 is left over. And by definition, that equals I. So this would be 4i. And we tend to make it with a little fish hook at the bottom there. So that's the final answer on this one. Now for this next problem, negative the square root of -9. We have to realize that we're going to use our PEMDAS here, and that radical is a grouping symbol, so it kind of works like parentheses. We've got to simplify that first and then make it negative afterwards. So we're going to make this negative and kind of think of it this way to remember that we have to do this part first. And we're going to -1, factor that out, times 9. So that's going to become negative. That 9 becomes 3, the square root of 9, and that -1 becomes I. So this is -3i. And then for the last one, it looks very complicated. We're just going to go ahead and use those rules like we have before and see what we can come up with. So we have 5 minus 2, and then we're going to take that square root of -25, so that's -1 times 25, and that whole thing is going to be over 10. So square root of 25 is 5, so this actually becomes 5 minus 2 times 5, because we've pulled that out, and that -1 is I. And then that's over 10. And I can break this up at that negative sign. So I have 5 over 10 minus, and 2 times 5 is 10i, and that's over 10. And 5 over 10 is 1/2, and that's going to be minus I. That's probably the most difficult problem in this whole slideshow right here. A lot of weird stuff going on. Now we're on to actually the last slide in this lesson, which is approximating complex numbers. And it looks really tricky, but honestly, this is probably one of the easiest parts of the whole lesson. What we need to remember is that we have that real part plus the imaginary part. I is going to stay I no matter what. So really we just need to find an approximation of the real part and then the coefficient of I, which isn't really the proper term, but it's a great way to think of it. So on this first one, 3 is the real part and it's going to stay as 3. If I take 4 times the square root of 15 and round it to 3 decimal places, I get 15.492. And that's because the next digit is a 9. So I'm going to leave it like that. I'm going to keep the I, and that's all they want you to do on this one. For this next one, there is a little kind of tricky thing going on here. So I am going to rewrite it as 3/7. It's plus a negative 1/7, so it's really minus 1/7 over I. Now, even though 3/7 and 1/7, it looks like it would be 2/7, it's not, because remember that 3/7 is representing a real part, that 1/7 is an imaginary part. So 3/7, that is approximately 4.429 minus 0.143 and then times I. That's all they want for that, and it's an approximation, so you can kind of get an idea of what those values are. So I will see you when we come back from Thanksgiving break. I hope this video helps you, and if you have any questions, the homework will be due after, so we'll have some time to fine-tune this.